Hello, welcome to your lesson on sequences. In this lesson, we'll be looking at applied problems. To begin, we will do investigation number 2. In class, we looked at investigation 1, which helped us discover two formulas, and this second investigation will also help us discover a key formula in applied sequences. We are given a table of population, and this is the population of Canada. Oh wait, did we say Canada? Oh, Canada. Well, let's pause right now because Canada is the greatest nation on earth, and I think it's important we sing the national anthem together. So let me jump ahead here. I think I have the national anthem ready. I mean, of course, you have these lyrics available with you all the time, but here they are just in case. Let's begin on 3. 1, 2, and 3. Oh, Canada, our home and native land, true patriot love in all of us command. With glowing hearts we see thee rise, the true north strong and free. From far and wide, O Canada, we stand on guard for thee. God keep our land glorious and free. O Canada, we stand on guard for thee. O Canada, we stand on guard for thee. Wow, that was incredible. So you are just standing because it said we stand on guard. So please be seated. Let's get back to our lesson. So we have the population of Canada. It is given here in millions. So this is 35.152 million and so on. You can see the population has been rising just slightly every year, not too much. Our goal is to calculate the growth ratio for population year to year. So what is the growth ratio from 2013 to 2014? Well, we see the word ratio in there. So that tells us maybe we're looking for an R value because that's what a ratio is, a multiplier. So how would you find the multiplier from 2013 to 2014? Well, as we know, we can use this formula. To find a ratio, we can do the next term divided by the previous term, right? This means the term following this one. So one term divided by the previous one. So in this case, we're going to do this population divided by this one to get our ratio. Divide those and we find out the multiplier between those two is this. So our growth ratio is this number here. All right, do that for 2014-15. So for the next 2 years, we divide those two values. So divide this one by this one, and we get a growth ratio of 1.008. So maybe now at this point you're thinking, oh wait, the ratio is not the same. Therefore, this is not a geometric sequence. Therefore, I can't continue. But that's not true. In real life, data rarely follows perfect patterns, right? We have to see what the data shows us, the real life data, and then make a decision to force our will upon it. So we're going to look at these ratios and see if they're close enough so that we can kind of say, well, it's close enough, and we're going to just call it geometric, right? That's what we do in math. We model real life data, and we have to do some little bending and twisting along the way. It's not going to be perfect. Okay, next one, 2015 to 2016. Divide those two values and you get a ratio like that. And finally, the last 2 years, we see the ratio is that. So we see that, yeah, the ratio did jump around a little bit, but it is pretty steady. So how can we determine, well, what's the ratio we're going to use? If we're going to decide that this is close enough to a geometric sequence, what ratio should we use? Which one of those? Well, the best thing to do is to do an average, which we'll do in just a moment. But before that, we're going to look at what do these mean in terms of percentage growth rate? So I want you to know the difference between growth ratio and percentage growth rate. Growth ratio is that multiplier. Percentage growth rate is what, if you were to say how much population grows year to year, what is that percent? So look at this first number here and decide, looking at that, how much did the population rise as a percent from year to year? The answer there is 1.1%. And we get that from right here, right? This one in the beginning represents 100%. All right, 100%. So that means to get this population to become this new population, well, first of all, it's going to be 100% of what it was, but then it also rises a little bit, and this is the little bit it rises here, that 0.011. And that it works out to 1.1%. Because 0.1 would be 10%, 0.01 is 1%, so this is 1.1. So how about the growth ratio in the next 2 years? Well, we can see it here. That's not 8%, be careful, it's one decimal over, so it's 0.8%. So the percentage growth rate is that much. How about the next 2 years? What's the percentage growth rate? Well, 1.2%, we can see it here, and here also 1.2%. So again, remember the 1 represents 100%, so when we're multiplying 1 year to the next, we multiply by 100% to get the same population, and then the additional bit, which is our percentage growth rate. Hope that makes sense. Let's continue. Oh, we did that already? All right, so now we have all these growth rates. Let's find the average growth ratio. So looking at all those ratios, find the average, because that's the one we'll use in our geometric sequence. Well, that average, you add them up, divide by 4, works out to about 1.011. So it ends up being kind of like the first one we saw there. So we're going to assume that's our rate. So then what is a formula or general rule you can use for finding the population growth in Canada? Well, here's a pretty good rule. To find the population, we take the starting population, I guess that was 2013, and we multiply by that growth ratio, which we used the average one there, and t here I'm going to use for the number of years that pass. T time in years, right? That's a good formula. Now use that formula to predict the population in 2025. So here's the formula. See if you can get the population prediction for that year. Well, the first thing to note there is 2025 is 12 years after 2013. So that means T must be 12. There are 12 jumps, right, from 2013 to 25. So the population is multiplied by this growth ratio 12 times, right? So there's the 12 here. And we get an answer of 40.08. So just over 40 million is our prediction based on that average growth rate. So that formula there leads us to a general formula for population growth. So let's write this in on our page as well. So we have that formula. That can be rewritten like this, P sub 0 being the initial population, times 1 plus this part here I just divide into 1 plus that, right? So it's like the 100% plus the growth ratio as a percent every year, and that times that. That formula is basically what we see here. This is a general population growth formula. It doesn't mean just population of cities or countries. It can mean population of cells in a bacterial culture or whatever, right? It's just growth in general of something. So here's initial, here's the population we're going to get in the future, 1 plus the rate, and then the number of times we're making the jump. All right, in here again, those are the things that represent the parts of the formula. So now we have 3 formulas. Let's recap the other 2 we had. In class, we looked at simple interest, and simple interest we saw was rising by the same amount every time, therefore it was arithmetic. We looked at compound interest, which was rising by a multiplier every time, therefore it was geometric. And we came up with arithmetic formula for simple interest, which we simplified to this. Take a moment and look at this some more if you didn't quite understand what's happening in class. Just look over this a little bit more, make sure you understand the details. And then we made a general formula for compound interest. That's where the interest is applied on the interest as well. That was geometric. Here's our formula. That simplifies like this. And again, that led us to these 2 rules. So I have a thing on the bottom of your page which says reminder and then these 2 formulas. So write them in one more time and maybe write any pieces you're missing during class. So now that we have these 3 formulas, the simple interest, compound interest, and population growth, let's use them to solve some problems. One thing you should note about this formula on the bottom first is, here's your initial investment. This is the rate per year, and this represents how many times per year you're paying out. So for example, if it was a 6% annual rate, you would put 0.06 there, and then if it was paid out every month, you would put a 12 here, because you're dividing that rate by 12. And notice the n is here also. So that means this is how many years pass in your investment, and then you multiply by the number of times per year that you're paying. So again, if you're paying every month, you'll put an extra 12 in there. You'll see how that works in a moment. So let's look at this first problem. It says somebody bought a car. They got a loan from the bank. The bank said you're going to pay us interest for borrowing that money, and it's 2.5% simple interest. So use the formula. How much will the person have to pay back to the bank? Okay, so there's the formula, and using it here, here's the initial loan amount, 1 plus the 5 years at this rate. Those become this number, multiply that. It tells you how much you will pay after 5 years. Okay, next one. Take a look at this one, and notice that this one says compounded monthly, so we're going to use the compounding formula. Remember that this represents how many compounds, so 12 per year, and 12 will go here also. Let's try. Okay, so here's the work. Since the interest is paid monthly, it says R equals this. So it's like your annual rate divided by 12 because you're dividing into how much are you, what is the rate for every month. But that shouldn't really be R there because really that's R divided by N. That R over N is this part here. So what that really should say is this is your monthly rate. Okay, so, but this is exactly what goes into the formula here. Here you see it, the annual rate divided by 12 payments, right, every month. And notice what happens to the exponent here, right? How often is this rate being paid? Well, it's being paid 12 times a year every month, but this is done for 4 years. So you do the 4 years times the 12 payments, once every month, means 48 payments in total. One time every month for 4 years is 48 payments. So that's what goes here. This rate is applied 48 times. So I hope when you think of it that way, the formula makes more sense to you. So here's our beginning amount. Here's the rate you're going to pay or get paid by the bank every month, right? Because it's the annual rate divided by 12. And then that happens 48 times because this happens 48 months in a row. So there's your final amount that you'll have in the bank. Okay, next one. Take a look at this one. See if you can solve it. Here we go. Using that formula again. This is compounding. It says, is this compounded? Also compounded monthly again. That's a very common compound situation every month. So this time you're told how much there will be repaid in the future. You're told how much the loan was in the beginning. And then it's like, okay, well, if that's how much they pay, and this is how much they got the loan for, then there must have been some interest rate that turns that 12,000 into that 16,000. So that's what we're looking for, the rate. So here we have 1 plus R, right? R, they're going to find the annual rate, and it's paid every month, so we divide by 12. Again, that rate or that interest rate is divided into 12 once for every month. And the 24 here, because it takes, 2 years to pay back the loan, and since it's paid every month, 2 years times 12, 24 payments. That's one time every month. Solve that backwards, right? Because you're solving for R, so get to here. What happened here? Okay, to get rid of this 24 here, we took the 24th root of all that, and that means the 24th root of that, and that's what we have here. That might be a little tricky algebra there, but that can be punched in your calculator. If you don't know how to do it, you'll press, I believe, the math button. Let me double check. Math, yeah, the math button has something where you can do a root and enter any value here, so it's not just a square root. That gives you this, solving some more using algebra, and you get a rate. Good problem. Make sure you know how to solve that kind of thing backwards here. All right, this one here, Oliver's savings account. Okay, compounded quarterly, so that means 4 times per year. So solving that, the interest rate then, the quarterly interest rate, right, because this is going to be the annual rate divided by 4. So every quarter, the rate will be this, and that's what goes in the formula. And since it's paid 4 times per year, and for 6 years, 6 times 4 makes 24 payments in total. So 24 goes here. And then you do that, and you're solving, I guess, for the initial amount that he deposited 6 years ago. We know the future amount, but we need to know that. So you're solving backwards for P. Yeah, pretty easy algebra there. Hope that worked out for you. And now we have 2 other word problems. Take a look at this one. It's hard to see here. Make sure you look at the one on your page. It's going to be easier to read that. Okay, so check all your work. Increase in population can be found like this. Population growth, taking the amount it grew by over the previous amount, that gives you the growth rate, okay, because that's how much it grew as a portion of the total. Then you have a formula, or U1 is here, R is what we just calculated here, and we have a general rule. So the initial population times 1 plus the growth rate, right, 1.005, and then the number of years. And in the final problem it says, I think, yeah, it says 2025, and we're going from 2015, so 10 years have passed, so we put a 10 here, and we get a population. Also, once you get the process here, it's not so bad, so I hope you're able to figure most of that out. And the last problem is this. You're creating a general rule for this, and then let's see if we can figure out problem C here. Okay, so check your work here carefully. I don't have much time to explain this. My 15 minutes is almost up, but take a look here carefully. Make sure you can make sense of that, and check your work there. Please let me know next class if you have some questions about this. Great work, and see you next time. Thing by GDC means graph this, two equations